Okay, welcome to the session on autonomous vehicles, and we're going to start right on time in respect for your guys' time, and some people might trickle in later, but I think it's the right thing to do for if we want technology to go forward, we should be on time, on technology at least. So let's start with this, that is a very famous phrase, that sentence that someone said, it's like, autonomous vehicles is the easiest of all technology problems nowadays, and it should be completely sorted out in a very, very short time. Said nobody else, right? This is not a simple thing, right? This is not going to happen. Everybody understands at this point that this is a super, super problem, super big problem, and that nobody individually is going to be able to solve this, right? So the question is, how can we maximize the brain power working on this that is one of the hardest problems on tech nowadays, right? And that's what we're going to try to see today. So my name is José de Oliveira. I'm the engineer leader for autonomous vehicles at Unity. I've been working with machine learning for quite a long time. Starting last year, we started a very concerned effort inside Unity to support the development of technologies, particularly simulation, to allow the development of autonomous vehicles technology, right? So the topic today is going to be how we're going to be building environments for autonomous vehicles training. Assumption behind this topic is that autonomous vehicles training can be done with synthetic environments, and we're going to talk a little bit about that. This is the agenda. We're going to start with some context. Show of hands, who works directly in autonomous vehicles technology right now? A few of you, some of you not. OK, great. Because we're going to start with a little bit of one-on-one on autonomous vehicles, but at least not to bore too much the guys that already know about that, but at least it's going to put us in the same page. Then we're going to talk a little bit about why simulation. And we'll start with the assumption that simulation is important, but why? We'll talk a little bit about what is Unity's role on this whole development, and finally, how Unity is intending to execute on this role. Start with context. What is Unity? Of course, you guys probably know about Unity. Is the world's leading interactive content development platform. And that's the book of that, which is an outstanding content that we created last year. And historically, yes, Unity has been very, very focused on game industry. But for a while now, we've been migrating from a game engine, right? Kick-ass one at that, to a real-time 3D platform, which is a much more engaging and challenging objective. So there are a few areas that we've been branching into: automotive, architecture, defense and aerospace, consultancies. And for the facts of today's talk, we're going to be talk a little bit more about the automotive. So how Unity has been organizing itself to work with automotive. So we created a Unity Automotive and Transportation team, right? And it's a worldwide team. We have people in each one of these green dots. And reason for that is extremely important to develop this technology in sync with the centers that are developing this technology, the companies, OEMs, and technology developers that are right now quite spread around the world, from Silicon Valley to China to Japan to Korea to Europe. You know, there are some very commonly listed players, but the ecosystem is way bigger. And there are players that are stealthy, there are players that are not stealthy, there are players that talk about what they do, there are players that don't talk about what they do, but believe me, it's a humongous effort right now going on in the industry, right? So I'll show you guys a little video that kind of showcases some of the things we've been getting in terms of automotive, not specifically to autonomous. And let's see this video. So what did you guys see there? So what you guys saw were pieces of each one of these 5 areas that we've been investing in Unity, right? One is product design, the other one sales and marketing. Sales and marketing, for instance, for those that don't know, is several car configurations. You know, when you're going to buy your car, that you play around with colors and all stuff. Yeah, there's a lot of this content that's built on Unity. Services training that has been saving a lot in the process, time and money for several companies to not have to fly engineers every time that a new car comes out of the design table, to fly all the engineers to a place to train them on the new car. They can be done that inside. HMI, infotainment, all the entertainment in the cars, and autonomous vehicles, which again is going to be the part that we're going to be talking the most here, right? So with that in mind, why simulate? A little refresher again for some, and this is how we see autonomous systems, right? Typically, you kind of subdivide them in functional components. There are components like controls that take care of the fine motions of the car. There are planning, which is from A to B, how the car goes there. It's not only from A to B in terms of one side of the city or the other side of the city, but also even should I overtake this car or not? So the decision-making of the car is done in the planning component. There's the perception, which is typically the most known pieces of autonomous vehicles, probably because it's the one that is the most investment right now, which is how the car is able to understand the environment around, how the car can see things and understand the other cars, pedestrians, and what happens around. And there's another piece which is getting more and more important these days, which is coordination, which is for autonomous vehicles with the ability of connecting to the infrastructure and to other cars in the street, how they can leverage this information to provide different ways of driving throughout the city. Some people have already seen some videos where scientists propose intersections in which there's no stoplights, because if all the cars are autonomous, they kind of coordinate among themselves and they can cross without crashing, hopefully. So this is one of the things in coordination. So those are not strictly functional boxes. They help us understand the problem. There are companies that follow the approach of literally separating these components. There are companies that decide to put planning and perception together and have a consolidated model, machine learning model or heuristics model to control that. But that's how we understand the problem, right? So specifically about perception, and within perception, the problem of computer vision. How typically people develop computer vision models? Well, they start with some initial set of data, right? And most of the times it's real-world data. So then after the real data is collected, they go through a process called annotation, in which a human being has to go, army of human beings have to go and mark each one of the important pieces of the content so that they can indicate this information to the machine learning training model. You typically separate a part of the data set to be your testing data set, and you use the training one to train your model, to test based on the testing data set. If it's below the target you expect for the quality, you keep on iterating until you're happy with that, and then you produce your model, and there we go, right? Now, what's the problem with this whole thing? This problem with this whole thing, and probably the weakest point, is this. For you to get data sets, you need to do the annotation. The annotation is expensive, is time-consuming, and it is not accurate, 100% of the time accurate. And if you don't have accurate information to give to the models, you don't have a model in the end that trains correctly. These, by the way, are all pictures, are real pictures of systems that have been developed for this kind of training. So, so the autonomous vehicle data problem, what it is, so you have to generate data sets to train your model, but typically the state of machine learning algorithms right now is that you require a lot of data. So And machine learning is the core for autonomous vehicles. It's the core for perception and core for several other parts of the machine learning. Collecting this data is expensive, annotating data is expensive and error-prone, and the most important piece, real-world data can only prepare the model for what has already happened. I mean, you do try to prepare the models in a way that it abstracts information away, but the reality, particularly when you talk about planning, which is dealing with different situations, you might incur in the problem that, well, I haven't seen that, I don't know how to behave. So I like this picture. I think this picture should be hanging in every autonomous vehicles engineer nowadays. It's like you look at this, and in the rear mirror, you saw a very dirt piece of roads, and you now believe that you've seen everything, right? Oh, I've seen everything. I know that the path ahead is straightforward and it's awesome, and my system is prepared for whatever it's thrown at. And then you bump into something like that in the real world, right? And I'll let you guys take a time, with the amount of craziness that can happen if you're driving around and a tank passes in front of you. I know, as a human being, I don't know what to do with this, right? I mean, if a tank just crossed in front of me. I got to believe that someone told me that this is a normal day in Russia. I can't comment. So in the end, why you simulate? You simulate because simulations can get autonomous systems ready for unforeseen scenarios and edge conditions in a fast and most important, cost-effective way, right? And let me give you an example of that. So this next example is not an autonomous vehicles example. This is a smart city problem. We partner with the city of Bellevue and the University of Automotive of Barcelona, CBC, the Center for Computer Vision. And the city of Bellevue had this problem. This video is going to be passing, and so I'm gonna show details later. But we partnered with the city of Bellevue, and they had this problem, and they have this vision called Vision Zero, which is how can we make our cities prepared in a way that we have zero fatalities in traffic, zero, right? It's not like one, it's not two, it's like zero. One way of doing that is to start with, you do not react when the problem happens. I mean, if a car crashes, if someone gets hit by a car, that's the statistics that the city uses to improve the transit system or the intersections and all this. But what if the city could turn events that are nowadays known statistics into statistics? For example, what if the city could get what we call near misses? So a car almost hitting another car, or a car almost hitting a person, and generate statistical data so that the planners in the city can do something about that before someone gets hit. And that's the idea. So the whole planning was to get the cameras that stay on top of intersections to recognize cars, recognize pedestrians, bicyclists, and then identify these critical situations and flag to the city that something happened. Of course, to generate this kind of data, to train models like this, based solely on the real-world data, is impossible. Why is it impossible? Because first, thank God, there's not that many fatalities in the traffic to start with. So you're not going to get in the real world the kind of edge case data that you need to train for. So what's the solution for that? So we decided to try to create super realistic, and I don't know why it's not playing. We decided to work towards getting real pictures of the city as models to eventually generate synthetic representations of those crossroads with full information about depth, semantic segmentation, everything, and full control. Once you have that as a synthetic data, you have full control to generate all sorts of different scenarios. So let me see if I can get this to play. So you can see everything that moves. It looks super, super real, but it's not real, right? That's the degree of fidelity, of visual fidelity that we achieved in Unity that helps this project to be successful. Because the cameras have to be fooled to believe that this is the real deal. And you can see everything that moves then is simulated. And because it's simulated, you can actually play around not only with the scenarios, but also with the placement of cameras around the intersections. So you can even now try to realize if there is a better placement of the camera that I need to do that improves my algorithm without having to send a crew down the road and change physically the camera from place. And then you can start providing the different corner cases and try to get your models training. This is an ongoing project, and hopefully we're going to have something to report down the road. So great. So we talked a little about AV. We talked a little bit about computer vision. We talked about how synthetic data can help. But what is Unity's role in all this? Back to that original question, how can we maximize the brain power working on one of the hardest problems on tech? How can we democratize the autonomous vehicles development? And we believe that we can do that by providing the best-in-class platform for AV simulation and data visualization, leveraging Unity's real-time 3D engine. The goal is to get something that is realistic, scalable, performant, flexible, and open. Those are the 5 tenets we are striving for. But does Unity build simulators? No, we are getting the same strategy here that we got with games, right, with the game industry. We do not build games. We can build reference models. We can build examples. We can build several things that help gamers extract the best out of the platform. But the actual application, the actual simulation is, we believe that's better done by the people that are working hard on solving the problem of AVs itself. So again, a little bit of refresher for some people. This is how we typically understand the automation levels. It's based on SAE, which is, what's it again? I forgot what SAE is. But the idea is between level 0, which is no automation, to level 5, which is full automation, there's a little bit of a gradation of how things go. And starting on level 3, things flip from being primarily driven by a human to be primarily driven by the car itself. And the problem with this shift is that the high complexity scenarios in this situation makes it economically infeasible to use established methods. So simulation for the auto industry is not a new idea. They have been using for a while, but the simulation tools that they have used historically did not evolve or became flexible enough to support the degree of complexity that we now have with autonomous. And that's the part that we believe Unity can truly help. So that's how we see simulation systems. Typically, we represent simulation systems. So if you look at this is what we talked before, right? This is control, planning, perception. Then all of this gets paired with the synthetic simulation environment in a way that you can provide ways for the autonomous system to be trained, validated, tested. We believe that Unity is particularly fit to work on a few areas of those: environment, sensor models, dynamic elements. Dynamic elements is things like pedestrians, like traffic modeling and things like that. And also the database of scenarios that we believe needs to be built in order to ensure that the cars reach a minimum level of quality before they hit the streets. In terms of the simulation workflow, so how you build these simulated systems? If you look from left to right, everything starts with content, with environments, is how you build your city, your synthetic highway, how you bring models of cars, you bring models of bicyclists. And then once you have all this content available, you need to start playing around with this. You start to build the scenarios, you start to play around with weather, you start to play around with time of the day, you start putting cars coming the wrong way, you start putting cars going like tailgating your main car. And that's how you start to generate the kind of data that you need for training the autonomous vehicles for the long run. But nothing of what you've done so far matters if this information doesn't make its way into the process of developing autonomous vehicles. And that's where the integration layer comes in. Integration layer here, we're talking about whatever data you have in your environment has to be perceived by the systems the same way the system would perceive the real world. So a good modeling of the sensors. Typically, people think about, oh, yeah, I can see cameras. We're going to have computer vision. Yeah, computer vision is one of the sensors, but we have LiDARs, which is laser-based sensors that can get much more accurate distance measurements for utilization. You have radars. You have acoustic sensors, the ones that you use when you park your car and they beep the hell out of you. Yeah, they can be applied for other things too. And then you have protocols, because when you simulate, when you have a simulation, you're going to eventually figure out if that simulation is working with the real hardware. So what we call hardware in the loop, which is connecting the real hardware with your simulation, is important. So supporting protocols. There are protocols in the industry right now, like ROS and other protocols. It's important for us to support those so that this integration is well done. And then there's the scalability, because you want to run your simulation in large scale. And there are physics, because you need vehicle dynamics, which are different from the things you can get with the ordinary physics in Unity. And then look at that. You have your whole system done, built, and now it goes to the street, and then something goes wrong. How are you going to debug that? We believe there is an angle here for utilization of AR and VR to visualize the data collected by the car once it's in the street, that I believe is going to be very useful to improve the quality of the vehicle as you go. And again, Unity can help a lot on these particular pillars, right? So how can Unity help the development of this tooling for autonomous vehicles? The three basic pieces of strategy we have is, one, incentivize the development community. Unity has a wonderful, wonderful development community with thousands and thousands of developers that they don't know yet, but what they do, the techniques and skills they have, can and should be applied to the problem of AV. That we believe deeply that by getting those guys focusing on this problem, we're going to get a lot of bang for the buck. I mean, these guys are going to be doing excellent work the same way they have been doing excellent work for games. The other part, too, is like in the platform itself, in the Unity itself, there are things that we need to be done that are specific to AV. And because AV is so dependent on machine learning, having also inherent support to machine learning in the platform is something that we believe it helps, and I'm going to talk a little bit more about that. And in the end, recognizing that the efforts, this is not an easy task to take. Autonomous vehicles is not an easy task, and it's not a cheap task either. The only way we can achieve this is with a very strong ecosystem of companies that can invest in the problem and extend the Unity platform and create the simulation solutions that will actually sort the problems. So going in each one of those, when you talk about incentivizing the community, it has to go through Asset Store. Asset Store is one of the best tools we have out there to bring the community to the creators. And in fact, if you go right now in the Asset Store, there is a curated list focused on real-world simulation. And these are a couple of examples, excellent examples of tools that people have been doing to create content that is very close to be simulation ready for those creating simulation solutions on Unity, right? Now, when you talk about improving the platform itself, the three big areas we think we need to invest are sensors, content, and integration. So I'm not going to read everything for you because you guys can see there. But the idea is that we need to increase the pipeline of content for simulation. We need to create ways for people to develop sensors. Sensors, in the end, is a kind of content, but it's more on the side of physically correct sensors, and it requires a slightly different skill sets than the other sensors, but we believe we need to lower the barrier for people to start producing good work there. And then finally, the integration, which is connecting Unity to everything else. In terms of how can we jumpstart some of these things for the guys that are starting but are not like fully funded like many companies that have been working AV, academia, or enthusiasts, we don't know where the good ideas are going to come from. It doesn't make sense for us to have this hard of a problem in which a lot of brain power has been going to waste because the guys don't have the right tools in hand, right? So how can we jumpstart by giving tools to these guys? One of the ideas is to seed some sample content, scenes and sensors. And this is an example of a LiDAR that we put together with some scenes we have. And we are intending in a short time to be able to provide free content and free sensors that people are going to be able to just drop into the Unity and have a minimal viable simulator that they can start playing around and go from there. And when they do that, they're going to have the full support of the Unity ML agents to help them develop the algorithms. ML agents is a wonderful thing that Unity has been developing. It's my colleagues in the machine learning team. And it allows you to use the very rich machine learning frameworks that are out there, TensorFlow, and also provides a set of tools that really bootstraps the generation of machine learning solutions on top of Unity, using Unity as the source of the training data, and particularly focusing on reinforcement learning, which is the ability of not only get all the information ahead of time and train your models, but also as you get the information, you react to what you're receiving, and then you learn with the reaction. Unity is perfect for this kind of stuff. One example of this application is called the imitation learning. And this is an example of the imitation learning. On the left, you have a human driving a car. And on the right is the machine learning how to drive this car. And it starts hitting the walls and all sorts of stuff. But as it keeps on watching what the human is doing, starts to pick up on what are the rules here, right? Oh, I should follow this rule. Oh, I should not crash. Oh, I should steer to the left when there is a curve to the left and to the right. So eventually, it learns to drive as well as the human. And in fact, this technique has been used in autonomous vehicles directly. There is a competition that happens annually for universities to create rescue autonomous vehicles. So if you are in a situation of hazard, if there is a building on fire or some sort of a natural disaster, and you need to shuttle people out of the danger, the idea is that you would have these cars that you could drive them once through these debris zone, and they would learn how to go, and from that point on, they would shuttle people in and out without adding danger for more people. And that competition happens is based heavily on imitation learning. And we you should be able to enable this kind of scenarios in the future. And finally, as I said, this is not an individual problem. It's not a problem that we're going to solve by ourselves. We need the support of companies. And in fact, we have already a reasonable number of companies invested in getting Unity, in using Unity to get a solution for the problem. These are some of those, and we are very proud to partner with these guys because all of them are top-notch in what they are doing. And all of them are pushing the envelope in what can be done with Unity we are making the platform better because of them, and hopefully we're making them better because we really believe in the mission that they have, which is build safe autonomous vehicles technology for the future. And with that, I'd like to thank you guys for being here, and I'd like to open for Q&A.
On the last slide that you showed, you had a IR simulation. Are the IR emitters built into those models, or how is that being simulated?
So LUMINAR is an interesting company. They are doing a kick-ass sensor. And what you're seeing here, if I'm not mistaken, is not even the simulator. This is the visualizer for the LiDAR, which is also built in Unity.
I'm asking about the one on
the one here. Actually, I have the guy from CVidia here, Miguel, if he wanted to give us a word on what he's been doing in CVidia for infrared sensors.
Yeah, so that's our thermal sensor. We are using a replacement shader, and then we created thermal distribution textures for the cars. For the rest of the scenario, we are, we are using the albedo color as a base, and we go on from that. And then we have like several effects that we've added on top of that to mimic the response from the real-world sensor. Like thermal noise and an inverse ambient occlusion to get that effect of the heat bouncing off the road. So yeah, it's just a composition of several different effects that we are using.
Great presentation.
Thank you.
So when you hear companies talk about driving, billions of miles, are they actually building billions of miles, or are they building like 1 mile and driving it 1 billion times?
It's an excellent question. So billions of miles don't matter, in the sense that, as I mentioned before, the most important for the models is to learn about those situations in which they need to react to something. So if you drive billions of miles in a straight line, your model is not going to be any better than a model that drives just a mile on that. So with that said, so they do create situations in which the cars go over and over and over, including boring pieces of highways, and they do, in the end, drive these billion miles. But the nature of the tooling right now is that building this content is expensive, and lots of the content is manually created. So these cars have a tendency of going through the same places over and over, and then what they do is that they affect the dynamic object so that they can create new scenarios on top of the same roads. Does that make sense? I mean, so yeah, it's the same road. Now, why did I say that miles don't matter? Exactly because of that. There was a workshop here in Siggraph specifically about AV, and it was very interesting. One of the hot topics there was this whole concept. There is a RAND Corporation, RAND Institute research that says that, we need to drive, I think the number is like 15 billion miles in cars, autonomous vehicles, before they get the level of security that we need them to be in the streets. And again, 15 billion miles of straight line doesn't take you anywhere. So this is not the right metrics, we believe, to use. The correct metric is scenario coverage, is how many different scenarios you get the cars exposed to. And that in itself is complicated too if you work with software and if you work with something as complex, for instance, as chip quality QA, right? If you're building a chip that has billions and billions of transistors, you cannot reproduce every single scenario that you can have there. Something very similar is happening in AV too. You cannot exhaustively have all the scenarios there. So the ongoing discussion is how can you create significant, meaningful scenarios that you trust that your car is safe, and what is meaningful, and how you measure that. So those are open answers, the open questions. They don't have any answers. Nobody's going to tell you that they know absolutely what's the solution here, but everybody knows that the more scenarios you can build, the more flexible your tools are to generate scenarios, the closer you are from a situation that you can trust that the car is going to do the right thing. Make sense?
Hello. In your slide, in the past slide, there is integration layers written. But I didn't quite understand what is VR and AR is used for in the integration layers.
And sorry if I went too fast for that slide.
Yes, this one.
So I think that the part that I didn't explain well was what I call the AV applications. And let me show you a slide that I was not going to show, but I can show here. So this is how we see the autonomous vehicle development cycle. So you start with a model, you create a model. It could be perception, so it's a computer vision model, or it could be navigation or whatever. Then you go through a stage of validation in which you check if this model is actually doing what it's supposed to do. Then if you're going to deploy these in the real world, we believe that there is a certification phase that needs to be done by a third party. So this is, you could think of this as being like the driver's license test for your car before it goes to the street. And then once it goes through the real world, you have to have ways of visualizing what the car did in that real world. If you get this data into a platform like Unity, what you get for free is the ability of providing visualizations in AR and VR, which means if you have a synthetic environment that represents the real world, you can replay what the car did, and you actually can place yourself in any part of that situation and try to understand in a more friendly way or in a more intuitive way why the car didn't break. Why is there occlusion here? I mean, you can represent occlusion in markings in your simulation, or you can be there sitting in the virtual cockpit of the car and understand that a particular element of the scene was occluding sensors, and therefore you have to work on the placement of your sensors. That's the idea of using AR and VR. Does that make sense?
I'm sorry, I'm the least bit technical. But I wanted to know if you use AR and VR to kind of provide test data to the vehicles to prevent accidents.
So again, we work with several companies that do lots of things. Unfortunately, I'm kind of bound by NDAs with some of these companies, so I'm going to be able just to talk generics here. But there are companies working exactly with that, particularly for insurance purposes, and I'll leave it in that point. But there are companies, and there's more development that needs to be done there in order to have a proper solution. But something is going on there.
Can you talk a little bit about using synthetic data to generate annotated data for machine learning training, and what sort of problems you may have encountered getting a machine learning algorithm to accept synthetic data and to properly do inferences on real world data?
Yes, absolutely. So the premise of using simulations the way we've been proposing here is, of course, is to get synthetic data to prime to improve the models. There's a lot of work done in terms of validating if synthetic data can improve perception, particularly. The initial work in autonomous vehicles done with Unity that I'm aware of was actually by the University of Barcelona, Automotive Barcelona. Some 3-4 years ago, they've done a synthetic data set called Cynthia that is open source and it's available to everybody. in which they wrote a white paper that proved that mixing real-world data with the Cynthia data set yield better computer vision models than using the real world by itself. All that said, one of the discussions we also had in the workshop on Sunday was regarding what we call the reality gap. So you have your synthetic data, and you train your models, and then you put these models on the real-world cameras, and then they don't perform well. Why? That's the reality gap. There are techniques that people have been using and trying to close this reality gap. Some of them goes in the direction of a hyper-realistic synthetic scenarios in which you try to reproduce camera imperfections and things like that, and they have good results there. There are some other people that go in the absolutely opposite, and they do what we call domain randomization, in which the synthetic data gets completely wacky when you look at that. But what they are trying is, knowing that the perception models have a tendency to generalize for common points, they try to take away from the generalization anything that is specific to color and try to get focus on shapes. But there is an ongoing discussion again on how close to reality the synthetic data is, how effective it is. There was a presentation by the guys in Zoox that they did a very good job of showing what they have been doing to prove that their synthetic data and simulation environment is capable of reproducing what the real world does. And I think similar work has been done around. But as with lots of the answers here, it's getting a little old when I say that. It's still an open problem and it needs more work to get. Did I answer that?
Yes, thank you.
Okay. Anything else? Okay. Going? Gone? Okay. Thank you guys a lot, and I hope you guys got information that is useful for you, and